Now let me explain to you this theorem, the fundamental theorem of group homomorphism, which is very important. Now the statement is like this: let f defined from G to G prime be homomorphisms of G onto G primes. That means f defined from G to G prime is not only a homomorphism, but it is also an onto mapping, which means that every x prime belong to G prime has a pre-image in G. And take K to be the kernel of f. The kernel of f, then in that case, what is G by K? The quotient group G by K will be isomorphic to G prime. Now what do you mean by this one? G by K is isomorphic to G prime means that there exists a mapping, say G defined from G by K to G prime, such that G is on 1, G is on 2, and G is a homomorphism. So let us prove this theorem. Now here, you define first a mapping. You can see this figure. This is given. Given G is a mapping from, given F is a mapping from G to G prime. Now from G to G by K, you can define a mapping theta as theta is equal to theta of x is equal to kx. Because G by K contain an element of the form kx such that x belongs to G. So let us show that this theta, the mapping theta here is an onto homomorphism. Theta is a homomorphism because we can, by taking these two elements, say x and y belong to G. What is theta of xy? By definition, because I define theta x is equal to kx, so it will be kxy. But k is given to be the kernel of f, and we know that in the earlier discussion, we have mentioned that k is a normal subgroup of G. So kxy can be written as kkxy, which is equal to kxky, because kx is same as ky, as k is a normal subgroup. So therefore, this theta xy is equal to kx into ky, which is equal to theta x into theta of y. So this implies that theta is a homomorphism, that is theta xy is same as theta x into theta y. Theta is on 2. This is clear only because for every element kx belong to G by K, there exists this x belongs to G here. Because this x is an element of G, you can see from the definition, such that kx is equal to theta of x. So this clearly implies that theta is an onto homomorphism. So now our aim here is to show that the mapping now G defined from G by K to G prime is an isomorphism, that is G must be 1, 1 on 2 and a homomorphism. So for this one, you define a mapping G from G by K to G prime as G of Kx, because the elements of G by K are from Kx such that x belongs to G. So G of Kx should be equal to f of x. Why we define element of G prime can be expressed as f of x? Because this is from the given condition. F defined from G to G prime is an onto homomorphism, which means that every element x prime of G prime can be expressed in the form of f of x. So therefore, every element of this one can be expressed or is expressible as f of x, because the mapping f from G to G prime is onto. So let us define the mapping now from G by K to G prime as G of Kx is equal to f of x. G is well defined. So let us first show that G is well defined. To prove that G is well defined, what we need to show now is that suppose it is just the reverse of showing that G is 1, 1. Suppose Kx is equal to Ky in G by K. So this will implies that Kxy inverse is equal to Kyy inverse. You multiply on both sides, but on the right by y inverse. So it implies that Kxy inverse is equal to K, because y inverse gives you E the identity and K is equal to E. And by the theorem on subgroups, this will imply that xy inverse belongs to K. So xy inverse belongs to K, but K stands for the kernel of f. So this implies that fxy inverse must be equal to the identity E prime, which implies that fx into f of y inverse is equal to E prime, as f is a homomorphism. So now here it implies that fx, and we know that fy inverse is same as fy the whole inverse by the property of homomorphism. There is a theorem that we have already proved on that one. So fx into f of y, the whole inverse is called to e prime, which implies that fx is called to f of y. And this is possible, if fx is equal to fy will implies that kx is equal to ky, because we define, g of kx is equal to g of ky, because we define g of kx as f of x. So now this shows that G is well defined. Now G is a homomorphism. Let us show that G is a homomorphism. So for this one, you take, let kx, ky belong to G by k. Then what is G of kx, ky? This is equal to G of kx, ky, which is equal to G of kxy, because xk can be written as kx. And then k into k will be k. So this will be g of kxy and it will be f of xy. And as f is homomorphism, so fxy is same as fx fy. And this gives you g of kx into g of ky. So this means that g is a homomorphism. Now let us show that g is 1, 1. So suppose this one, you take kx, ky belong to g by k. Suppose g of kx is equal to g of ky. I need to show that kx must be ky in order to conclude that g is 1, 1. So this will implies that fx is equal to f of y, because I defined the mapping gkx as fx. So gky will be f of y. And this will implies that, okay, fx is equal to f of y. This will imply that fx multiply on both sides but on the right side by fy the whole inverse. Fy the whole inverse is equal to fy into f of y the whole inverse. And this will implies that fx, but what is fy the whole inverse? It is same as f of y inverse, and on this side fy into fy inverse will give you e, the identity element, e prime. It is e prime, the identity element in G prime. So this implies that fxy inverse is equal to e prime. As f is a homomorphism, so fx into fy inverse will be same as f of xy inverse. So this gives you e prime. Now if it is e prime, this will implies that xy inverse belongs to k. As k is equal to kernel of f, this contained elements x belong to G such that f of x is equal to e prime. Say a such that fa is equal to e prime. That means kernel of f or k contain only those elements of G which are mapped to the identity e prime of G prime. So now here, from here we have xy inverse belong to k. So if xy inverse belong to k, it implies that kx y inverse is equal to k. Again, by the theorem on subgroups that we have done in third semester, kxy inverse must be equal to k, and then multiply on both sides but on the right by y, then you'll get kxy inverse y is equal to ky. This one will give you the identity. It implies that kx e is equal to ky, which means that kx is equal to ky. So this implies that G is 1, 1. Now only thing left is to show that G is on 2. So what we need to show is that the mapping G defined from G by k to G prime is on 2. That means every x prime belongs to G prime must have a pre-image in G by k. So let x prime belongs to G by k. Then we know that for x prime belong to G by k, their x belong to G. You can see from here, because f is given to be an onto mapping from G to G prime, such that x prime is equal to f of x. Now, for every x prime belong to G by k, we are having an x in G such that x prime can be written as f of x, because given that in the statement it's given that f is on 2. So this is possible because f is on 2. So x prime is equal to f of x for x prime belong to G. But what is fx by the definition of mapping defined from G by k to G prime? It is G of kx. So this implies that x prime is equal to G of kx. So which means that every x prime belong to G prime has a pre-image kx in G by k. So this implies that G is on 2. Now hope the explanation on this fundamental theorem is clear now.